So, welcome back, and this will be lecture 12. Sparse arrays is the topic, as you can see from the slide there. The idea of sparse arrays is going to sort of conclude the linear structures. The next three lectures will be on trees, different forms of trees, and then those three lectures will be the last three before the exam. I'll have more up before the exam, and I do apologize again for the delay on these recent bunch of lectures. But the idea will be that we end with binary search trees. That'll be the last lecture before the exam. The exam, I'm not sure when you're all taking the exam, but assuming it's on the same day as we have it here, it's 2 weeks from today. I'm taping this lecture on Wednesday the 20th, which is when I actually gave the sparse array lecture in class. So this is today's lecture. I've just got to put up the slides together for the previous ones. But then the next three lectures, Friday the 22nd, Monday the 25th, and Wednesday the 27th, are the last three before the exam. And everything else after that won't be for the exam, but yet there'll be another week of lectures. And so you'll have plenty of time to sort of study over these lectures and get used to them. Same thing with the local students. The last section before the exam will be the fifth section, which will be sort of reviewing binary search trees. That section will be running from Wednesday the 27th here locally. The TAs will be doing that Wednesday the 27th through that following Tuesday. And then the exam would be the Thursday. We're not the 4th, I'm sorry. Thursday the 5th is our exam. The 4th is my other class. We're Thursday the 5th, so I don't know if you're perfectly in sync with us as far as when you take that or what. I don't know the details involved in that proctoring. But anyway, so the section then, section 5, you'll have the opportunity to view, and that will basically be reviewing everything. We'll talk about binary search trees a bit and binary trees, and then we'll sort of, in a sense, do a sort of a brief review of the major concepts up to this point, including the stuff I've done in the lecture and the PSP stuff and some of the code from section. So those are the things to keep your eyes open for. Adam has recorded section 3 yesterday. I actually, at this moment, I don't know if it's on the web or not, but it will be soon. And then he'll record sections 4 and 5 soon, and then you'll have all that material to study. So those are the things you're worried about for the exam. Charles and I are going to tape the binary search tree, the binary tree or tree lectures this weekend. And so the plan is, now that the hard drive's fixed and blah, 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 to have things getting ahead of the game, as we were just starting to do last week before the hard drive went down. And so our hope is that by Monday morning, we've got Monday's and Wednesday's lectures posted, and then you're all set for the exam as far as lectures that need to be up. And I think that's it. So as far as announcements go, that's the announcement. And what we're going to be dealing with now is sparse arrays, which, as I say, concludes the idea of the linear structures, the structures where you have sort of, in a sense, a predecessor and successor, instead of how we'll be changing that is we'll see with the tree lectures. Arrays are a little bit different because as soon as you start expanding things into multi-dimensional arrays, you have, the predecessor-successor relationship is a little odd. But when you're certainly dealing with single-dimensional arrays, you have a cell, and it's got a cell before it and a cell after it. So the same thing sort of applies for arrays and lists and stacks and queues. What we've seen up to this point was a sort of 3-lecture study of the list ADT, where we looked at how we could implement the list ADT using array memory, contiguous memory, or linked memory. We also saw the same things for stacks and queues. But for the array, we've only looked at contiguous memory. The whole point of arrays is usually to optimize the reading or writing of a cell based on an index, the operator bracket. And so in order to do that, you would need to have a contiguous memory implementation. It seems like it's, case closed, we use contiguous memory. But there are times when we would want to use linked memory to represent an array, which now completes the circle because that's the last thing we needed to look at. We looked at both array and linked memories for the other 3 structures, list, stack, and queue. Now we'll look at linked memory for an array as well. And so one of the motivations here, just to provide an example for a possible motivation, would be, let's imagine we're trying to model some section of outer space. So since, life is 3-dimensional, this model will be 3-dimensional. And whatever region of space we're trying to look at, let's say we break it up into 100, measurement 100 ticks on the side. So, whether this is 8 light years or whatever the heck it is, we'll divide it up into 100 units, however those units are. And same thing here, and then same thing with the third axis. So we have basically a cube, 100 units on the side, that spans some area of outer space. And what we're concerned with doing is within the range allowed by the fact that we're dividing our 8 light years or whatever it is into, or not 8 light years maybe, but 8, whatever the range is. We only have so much accuracy because we're only dividing it into 100 different pieces. If we're going to divide it into 1,000 or 1,000,000, we'd have more accuracy. But we have a limited accuracy here. But to whatever degree of accuracy we have by dividing our region into 100 sections here, we're going to try and locate the center of a planet, because we're concerned about where the planet is located. And let's say we have 10 or 12 of these planets. We'll say, okay, maybe one of them is located at, let's say this is 5, and this is 90, and then maybe it's located inwards a little bit along this axis. We can say, okay, that's located now, maybe this is 10. And so we say at 5, 90, 10, if this is the x-axis and the y-axis and the z-axis, then we say at this point, which is 5, 90, 10, maybe that's where one of these planets in space is located, at 5, 90, 10. And maybe I've got some other planet located here, and some planet here, and some planet here. And scattered about this region of space, I've got maybe 10 planets. So we have here 10, which means 10 of these coordinates will store the center of a planet. We'll have one at 5, 90, 10, and at some other coordinate triple, we'll have a second planet, and at some other coordinate triple, we'll have a third planet. And the problem here now is, well, if I've got an array that's 100 by 100 by 100, that's 1,000,000 cells. Only 10 of them will store planet info. That means that we have 999,990 cells that store nothing. And when we talked with a W linked list about how saving every last bit of memory is not necessarily a vital thing to have to do, what we're talking about there is saying, well, if we have n elements, if we have an extra pointer for every element, it's one extra memory cell for every element. That's not too big of a deal. That's just basically using proportional amounts of memory. You're saying, okay, I use 1.5 amounts, 50% more memory than perhaps I would have. If I have 100 cells, I use now 150 memory cells for 100 values instead of just 100 cells. But the point is, it's sort of a proportional memory usage. Those kind of things are not as big of a deal here. Where this situation, this is way to the other extreme. We have a few legitimate pieces of data, and in order to store them, we are wasting an astronomical amount of memory. No pun intended. So what we have here is the need, perhaps a need, if we have all the memory in the world, perhaps we can deal with that. But there's a strong motivation here to somehow reduce the memory usage of this structure, to store these 10 planets in a way that still gives us this conceptual picture, still allows us to access these planet locations as if we were dealing with a 3-dimensional array, but yet at the same time does not really implement this using a 3-dimensional array, because we're saying we're using way too much memory there. So we like the idea of saying, okay, here's a region of coordinate space and I pass some coordinates. The appeal of thinking about this as a 3-dimensional array is nice. That's the ADT idea. The array as an abstract data type, where that's our interface pretends it's an array. Behind the scenes, it doesn't have to be. It's been so up to this point, but if we were going to come up with different implementations that would save that memory rather than allocating all this massive memory when it was never going to be used, then behind the scenes, the implementation would not necessarily be a C++ array or our array class or whatever, yet we could still use an interface and present that picture to the user. And that then will be the idea of a sparse array implementation. The idea will be that when we have a sparse array, which I'll formally define in a moment, we can implement a sparse array using techniques other than just a 1-dimensional or 2-dimensional or 3-dimensional C++ array. And we can then potentially save memory at perhaps, usually, the expense of our bracket operator would now no longer be constant time. So the interface simply deals with correctness. The actual speed of the various algorithms that the interface is enacting, that's an issue of the implementation to worry about. When we talk about saying that we can swap implementations in and out without any problem, what we're saying is that each implementation needs to correctly support the interface. this will be a situation where we'll be putting in a new implementation that will make one of the speed of one of the operations worse. But the trade-off will be we'll save memory. Just like when we went from the array implementation of the list ADT to the linked implementation of the list ADT, back one, the idea of moving current backwards one, got worse. But insert and remove got better. So there was a trade-off there, but by moving a new implementation in, yes, one of the implementations of the interface functions ran slower than it would have. The interface doesn't care about that. What you care about in terms of calling the interface is making sure the interface is working correctly. But the implementations, you will naturally have different speeds and memory usages for different implementations. That's the whole point of being able to swap in implementations. My point with this long ramble is that it's not valid to say, oh, we can't talk about what we're about to talk about because that makes the operator bracket run slower. That's okay. Just like it was okay to replace the array implementation of the list ADT with the linked implementation of the list ADT, even though it made back one run slower. There's nothing that says that it's bad to replace an implementation with another one simply because the second one makes certain operations run slower. What we hope, however, is that by taking that penalty hit, we have improvements in other areas. And for the replacement in the list ADT, it was we gained speed for insert and remove, gave up speed for back one. Here we're giving up speed in operator bracket, but we will gain better memory usage. So, but there's nothing wrong with replacing an old implementation with a new one and having certain things suffer. In fact, certain things probably will suffer when you replace implementations. What you hope is that, firstly, other things gain, and secondly, that those gains are worth what you lose for your particular situation. And often for a sparse array, those gains will be worth what we lose. The gains in memory savings will be worth perhaps a little bit of increased time for operator bracket. Especially if we have a small enough number of values, then an increased time for operator bracket still won't be too increased anyway because we would have so few values anyway that it wouldn't matter. Though that won't always be the case. But anyway, that's the motivation for sparse arrays. I am probably not using the correct formal term for operator bracket. It's array access operator or something like that. Operator bracket is convenient slang. So bear with me on things like that. So given that now, let's define a sparse array. A sparse array is an array in which the amount of meaningful data is far less, not just less, but significantly less than the number of cells given. So as in the previous example, we had 1 million different cells in the array that could be independently indexed, and yet only 10 pieces of data. That's a very severe case of a sparse array. So this is what we have to deal with. In situations where we have far less memory being actually used than we've allocated for ourselves, that's a strong candidate for replacing with an implementation that is allocating less memory and therefore wasting less memory. The non-meaningful data we will give the term no elements. And at this point, I'd like to mention, even though between the lectures and the packets, the notes packets on the web page, that basically covers all the vital details of the lectures. If you want to start using the book, up to this point, the book has not been useful, but at this point now, the kind of things I'm talking about will, for the most part, be in the book, though not always, or maybe not always in the same way that I'm conveying them here, but certainly sparse arrays are. And so if you look over chapter 5, especially the beginning sections where you have arrays as opposed to strings later on, if you do have the book, chapter 5 in the book basically goes over the same things I'm discussing here. So you don't need to. I mean, the lecture is decent. As I mentioned in the beginning of the class, the book is more or less almost considered recommended rather than required. But for as far as that goes, you can see the sparse array material in the book as well as looking at it on lecture or in the packet. The other thing I guess to mention at this point before I move on is traditionally the sparse array packet has been handwritten. I hand wrote some notes way back when I first started lecturing this course as opposed to being a TA, and I've never converted them to online format, which is why if you've seen the web page, you may see that the sparse array and the tree packet say available at TAS and Granger. That's our local copy shop and bookstore, or I'm sorry, copy shop and reserve desk at the library, respectively. I am going to make an online packet for you. I know you folks don't have really good means of getting that stuff. And so since I need to make the diagrams anyway to post these slides up as your lectures, I will go ahead and use those diagrams then, since I finally will have the diagrams, I can then put those together in an online packet of sorts. So the ones that say, oh, it's handwritten, don't worry about it. It'll take the weekend. I'll have to work on it over the weekend. But you will have the packets online to be able to use. And so I finally will be converting those to online format as opposed to handwritten, mainly because I have to do those diagrams anyway for you folks for these slides. So loosely related to the book issue is the notes packet issue, and I thought this would be a good time to mention that as well as an aside. That said, back to the lecture. So the term null elements is what we're going to use to determine and describe meaningful data. Meaningful data will be whatever it is we're actually trying to store, and then these vast areas where the data isn't really meaningful will be called null elements. And we can best define meaningful data by explaining what kinds of non-meaningful data we might have. So the question is, as far as null elements go, what kinds of handling might we have for a null element? If we're trying to access a null element, if I pass in, an array index or a set of indices, if we have a multidimensional array, and those indices point to an element that doesn't contain meaningful data, such as in the previous example, pointing to an area of space that didn't contain a planet, how do we handle this? What results do we send back to the user in that case? And there are at least three things we might do, and I'm going to discuss those three things right now. By far the most common would be to deal with a default element, or default value, default element or default value. And the planet situation would be a great one. The meaningful value is there's planet data at this index set. The default value is there's no planet data. So there's no particular harm in accessing a null element cell. It just what returns back is nothing. And so perhaps if we had an array of all pointers that held pointers to data, we'd have 10 pointers that actually pointed to planet info records of some kind, and the other over 999,990 pointers would all point to null. But the idea then would be we would be sending back to the user some notification, a null pointer or whatever else, that says, oh, this is just a region of empty outer space, no planet here. So that's sort of the default. Another example would be if we're setting up a two-dimensional array to deal with polynomials. We have here is our polynomial number, so we have maybe 1 or 2 or 3 or 10 or 16 polynomials. And then up here would be a degree, the degree of the exponent on the polynomial term. So you can have a deeper array than this. I'm just going to show 2 rows, but certainly we could have many more rows. And here we have 0, 1, 2, 3, 4, 5, 6 in terms of columns. And so the degree means, for example, let's say our polynomial 1 is going to be, say, 5x to the 5th plus x 3x. Now what that is, well, the degree 5 term has a coefficient of 5. The degree 1 term, because x is just x to the 1, has coefficient 3. All the other coefficients are 0. And of course, this could continue on like that. Likewise, if I have a second polynomial that is, say, 2x to the 6th plus x squared minus 10, then I can say, well, that's not a problem. Coefficient of x to the 6th is 2. Coefficient of x squared is 1. Coefficient of x to the 0, which is what this is, because x to the 0 is 1. Anything to the 0 is 1. So this is really 10 times x to the 0. That's negative 10. And the rest of these are 0. So if we want to represent a series of polynomials of potentially very large degree, that does not necessarily mean we will have every single term inside the polynomials. And so some terms will be active. The rest would all have 0 coefficients to indicate, if the coefficient is 0, then the term isn't there. So if I looked up if I'm going to represent this now as a sparse array, which it would be a good candidate for because we'd have mostly zeros, What I could do then is say, if in my sparse array implementation, which of course we haven't talked about yet, but when we do, if in my sparse array implementation I actually find the cell, say 1, 1 or 2, 6, then I would return that coefficient. Otherwise, if the cell has not been given memory in my implementation, I send back 0. Just like in our planet example, we could store just simply 10 pointers to the 10 planet records, and if I didn't find the appropriate index set looking for it, I'd say, well, then this index didn't point to a planet, I return null. So the idea of a default value says, forget about actually storing those zeros, but if we look up a cell that would have held a 0, and therefore then that cell is not implemented in our implementation because we didn't want to store the memory for the 0, then what we should do is by default return a 0. So that's by far the most common way in which this would be handled, to simply say, well, if the cell hasn't really been given memory behind the scenes, then it meant it was supposed to hold a default value, and you can send back that default value. Second thing we might do is we might actually have an error returned if the element was non-existent. So let's say I'm using, just as an example, let's say I'm trying to model all the white squares in a checkerboard. So for whatever reason, I just care about the white squares. I'll just do a 4x4 one here. So this is a dark square, blah, blah, blah. And let's say I only care about the white squares. So I care about 1, 2, 1, 4, 2, 1, 2, 3, 3, 2, 3, 4, and 4, 1, 4, 3. Those are the white squares. And so in this application, dealing with just these white squares for whatever reason, technically I should never want to access one of the darker squares in the checkerboard. There should be no reason for me to do that. So if the user then says, hey, give me A of 1, 1, that is, according to even the conceptual model itself, an illegal access. And that's very different than the other two examples. For both the region of outer space and the polynomial, if I asked in polynomial 1, what's the coefficient of x to this x squared? That's a perfectly reasonable question. The coefficient happened to be 0 in that first polynomial, but it's a reasonable question to ask. Likewise, if I have this big region of outer space and I say, what's the is there or is there not a planet located at 2, 1, 20? That's a reasonable question to ask. The answer is there's no planet there, but it's a perfectly reasonable question to ask. Or if I say what's located at that dark square, that's not a reasonable question to ask because that conceptually doesn't exist. We're only concerned here with really drawing it like this in a sense. We're concerned with these squares. And so this square does not really exist, and we shouldn't be asking about it, even though it's, in terms of ordering the white squares, it's helpful to think of them as an array. So I can say, oh, this is 2, or 1, 2, 1, 4, 2, 1. Kind of dealing with these in the array model is a helpful way to index these cells, but I don't really want to be dealing with these dark cells. So this should produce an error that should say, sorry, that's not allowed. And so whatever sparse array implementation we dealt with behind the scenes, whether it, perhaps we dealt with some implementation that somehow saved half the memory, or whatever else it is we did, conceptually, that would be a situation where certain cells simply don't exist, and if we try to access them, we should return an error, not because the implementation behind the scenes, whatever it might be, doesn't store 1, 1, but because conceptually we don't store 1, 1. So the implementation certainly isn't going to store it, but this is unlike the previous example where the implementation didn't store it, but conceptually it did exist. So the implementation was not at liberty to toss out an error message because it was supposed to be there, and the implementation needs to then recognize that. Here it's not supposed to be there, so there's no trouble throwing out an error message. And the third type of element, or the third type of way in which we might handle this, would be not to return some default value or to say, hey, it's an error message conceptually doesn't exist, but simply instead to say, well, in this situation, calculate the value from other elements. And the ideal situation for this example would be a symmetric matrix. So I'll just draw a short 3 by 3 symmetric matrix here. 1, 2, 3. A symmetric matrix is a matrix in which A of I comma j equals A of j comma I. A matrix is, of course, just a two-dimensional array, or a square two-dimensional array. I guess it doesn't have to be square, technically. But anyway, that doesn't matter. I'm just babbling. So we have here, here's a symmetric matrix. The diagonal elements can be whatever they want, but now 2 comma 1 is equivalent to 1 comma 2, 3 comma 1 is equivalent to 1 comma 3, and likewise for 3, 2, and 2, 3. What this means is that if I had an implementation behind the scenes, and we'll discuss it near the end, if I had an implementation behind the scenes that could represent memory like that, in other words, I could allocate just those 6 cells and not the full 9. If the client tried reading that cell anyway, it's not a problem. Because if the client tries reading that cell, all I do instead is reverse the indices and return the value in that cell. It's the exact same value, by definition. So if we know by definition that a symmetric matrix would hold in this fashion, then I could not represent the entire upper triangle of the matrix. I cannot store that in memory. And anyone that tries to access one of those cells, I simply return this one. And that's the same value this would have been if we allocated memory for it. So I can avoid allocating memory for a number of cells. And the values that they would hold would simply be values stored elsewhere in the array anyway. And there are other situations like that too, where we would have some means of certain elements could be calculated from other elements. And so I then only need to store the minimum set of elements necessary to guarantee I can reproduce the entire array. And in this case, I need to store the diagonal and everything below it. Once I have those things, I can then reproduce the array simply by copying the below elements into the above spots as well. So that would be the third way to deal with this. So those are 3 different ways in which we might handle the null elements. And the then meaningful data would be any data that would be stored no matter what. And then the null elements would be the data that we would look at replacing, that would be dealt with via a default element or an error condition or calculated from something else somehow. So that said, now it's time to look at how we might actually implement these things, which is a little more of an interesting question. And we can deal here with, well, firstly, let's deal with 1D arrays. That's a little boring, but that's basically what we've been talking about all along here, the idea of a singly linked list. So if I have an array where I have index 1 contains H, and index 256 contains G, and index 10,868 contains the element C, and maybe overall we have 20,000 cells. Only 3 of them are active here. So here's my array A, for example. If I access A of 1, it should return to me H. If I access A of 256, it should return G. If I access A of 10, we'd have to decide, well, what happens there? Let's assume we have a null element of or default element of a null character. So we have the null character otherwise, that character. So that means then if we move this to a default implementation, or a sparse implementation, the null character would be the default element. We'd say if I'm not storing the actual cell, then return the null character. And so the way this could be dealt with in a list, we have here a head pointer. We would need to store not just the element now, but the index, because we need to know which index is associated with which element. So my individual nodes would need to store the index and the value, as well as a pointer to the next node. And then here we have 256 and the value G before dealing with a pointer to the next node. And then my third node would store 10,868 and the letter C and a null pointer. So there's my 3-element linked list corresponding to my sparse array, which held only 3 meaningful elements. And so if I'm going to now do the bracket operator, A of X, for reading, if I'm just trying to read A of X, what would be involved there would be whatever index X is search the entire array for it, or search the entire list for it, rather. And if I find x, great, then return that value. And if I don't find it, then return the default element. That would be dealing with it as far as reading. If I'm trying to deal with it as far as writing, a of x equals x, for example. Let's say a of 50 equals x. Well, if I was saying a of 1 equals x, or a of 256 equals x, or a of 10,868 equals x, I would be searching for one of those indices, I would find it, and I would overwrite the letter in that node with x. So if this is a value that was already meaningful, the index, we're simply going to find that index and overwrite the old data with the new data. If, on the other hand, that was not a meaningful piece of data, when we're reading, we simply return what's there, which would be the default element. When we're writing, we say, well, now we're adding a new meaningful piece of data. We're saying forget the default element. Essentially, we're overwriting the default element, as we would have if we inserted if we wrote to a of 50 here. If the character that used to be there was the default character, and we instead wrote x there, we're writing over the default character with x, the null character with x. And so in this case, we'd be doing the same thing. We're saying forget about the default. I actually need to insert this element into the list here. So we have 50, x, and a pointer, and then this would move up here, and this would come down here. And now we have 1, 50, 256, and so on. So for writing, we would either read the value associated with an index or send back the null element. For reading, we would either read the value associated with the index or return the null element. For writing, we would either overwrite the value at an index or add a new node to the list. Now you'll notice here the list is sorted. In general, when we're dealing with linked lists, there's a trade-off between sorted and unsorted lists. The sorted version can possibly optimize lookups or find searches on the list. We can't improve the order of growth. Ultimately, an unsuccessful search could take us to the end of the array no matter what, or end of the list no matter what. But if the list is sorted, or even if it's a sorted array, if we're dealing with an array, there's always, if it's sorted, then we have the idea of a bumper, where, for example, if I'm looking for the spot to put 50, as soon as I hit 256, I know, okay, I shouldn't move further, 50 should have been before this. So since I've passed up 1, which was less than 50, and now I hit 256, which is greater than 50, that means 50 should have been in between them, and since it's not found. And we were able to determine it's not found before searching all the way to the end of the list. So that's the upside to a sorted structure, is we can search a sorted linear structure, and when we pass up where the element was supposed to be, we'll know immediately by reading the next cell. Where if the structure was unsorted, then if I'm looking for 50, I need to look at every cell. 50 could be potentially the very last cell in the list or in the array. And so I would need to search and look at every single element, as opposed to just searching until I reach an element greater than that. So while it doesn't improve the order of growth, it will tend to increase the actual timed times, or decrease the actual timed times of lookups. We would, on the average case, only have to search down about half the list. And so that would be far more likely what would happen, where for a unsorted list, an unsuccessful search would definitely require searching the entire list. On the other hand, in general, unsorted linked lists allow you to just dump a value anywhere in constant time, where a sorted linked list would require you insert the value in the appropriate spot. And that would be a linear search versus a constant time insertion for the unsorted list. So traditionally, the trade-off is unsorted lists would require you search the entire list to do a search, but would allow insertion anywhere you want, and so there's constant time for insertion. Whereas a sorted list would perhaps improve a bit the running time of a search, but would require an order n insert because you need to search for where the insert is supposed to go before you do that. That's traditionally the trade-off between unsorted and sorted lists. Now, with that background, I'm going to avoid it by talking about this situation, because this is not a traditional situation. That trade-off I just gave you should be one you think about and deal with in a number of situations. But it doesn't apply here. Here, sorted list is the way to go. And the question is, well, why? And I'll give you a second to think about that. So pause if you want. The answer here is, because I'm searching for an index, I have to search anyway for something like a write in this case. If I want to insert x into a of 50, I have to search the entire list anyway to see if 50 is an existing node before I can go inserting 50 where it belongs. So if the list was unsorted, I would do a linear time search of the entire list, checking if each node was equal to 50. And when I find out none of them were, then I could dump 50 anywhere I wanted. That would still be worse than simply searching a part of the list, realizing 50 doesn't exist in the list when I go past the index 50 and see 256. And then I insert 50 right there. So because I have to do a search anyway with every potential insertion of a node, every potential insertion first requires we search and determine that index is not in the list. Because of that, there will never be a, oh, just dump the new node anywhere situation, because we would have had to do a search first anyway. So for that reason, we may as well go ahead and use a sorted list, even though traditionally the unsorted list would have some advantages as well. So that said, that then is the way we would implement a sparse one-dimensional array. We simply implement it as a linked list, and we've now talked about some of the things involved there. Far more interesting is the two-dimensional array situation. And we're going to look very quickly at 4 possible implementations for this. The first one is going to be, again, a singly linked list. So imagine dealing with a two-dimensional array here, where here's the number of rows, and here's your columns. There's no reason you can't implement this with a singly linked list. What you would need is to have the row number, the column number, and the data, as well as a pointer to the next node. So now, however many multiple dimensional array we have, in this case a two-dimensional array, you need, however many dimensions you have, you need that number of integer indices plus your data itself. So in a two-dimensional array, we need 2 indices and then the data, and of course that would extend to more dimensions. Now, what we would commonly do in terms of arrangements here would be to deal with things in terms of all the row 1 nodes. So we have here, maybe row 1, 5, x, and some pointer, and this would be then 1, 8, c, and some pointer, and then those would be row 1 nodes sorted by column. And then maybe after the row 1 nodes, maybe there's no row 2 nodes, and so we have a row 3 node, and so this would be row 3, column 1, and then maybe the value here is h, and then there's a new node. And so then we'd have row 3 nodes within row 3 sorted by column, and so on and so forth. The row 1 nodes, if any, the row 2 nodes, if any, the row 3 nodes, if any, the row 4 nodes, if any, and so on and so forth. Basically, the idea would be, for whatever meaningful elements are located in this array, basically traverse row by row. And as you pick up the meaningful elements, insert them into a list. That would be the way, one way to sort these elements, sorted by row, and within the row, sorted by column. So that effectively becomes a row by row traversal. Traversing over this list from front to back becomes effectively a traversal of the array row by row, ignoring the default elements or the null elements. So the question is, what's the access time? And if we have our rows in C columns, then our lookup, based on index, would be, well, how many potential elements do we have here? We have a potential number of elements of R times C, if we have R rows and C columns. Now, we probably have far fewer than that, but the idea would be then all that means is the constant in front of this would be very, very low. But in terms of the order of growth, as the product R times C grows, the linked list would tend to grow as well. So if I have, let's say my sparse array contains 1/10,000th of all the possible elements, well, if R times C increases, 1/10,000th of R times C would also increase. But the idea would be the worst possible case of this linked list would be if every element was stored in the linked list. And of course, then it wouldn't be a sparse array. But anyway, that's the worst case. Every possible element in this linked list, that's R times C. And if we have some fraction of the possible elements, then it's some fraction of R times C. And as the number of rows and columns grows, the product R times C grows, and the fraction of that represents our sparse array would grow accordingly. So the worst case for lookup here would be R times C, or order R times C. And the memory usage here is 2 ints and one pointer plus our data, all of that per cell. And I'm just running out to draw comparisons with future structures. So the idea is that our lookup is r times c. The memory we use is 2 ints, a pointer for the next field, and our data for each cell. So keep that in mind as we look at the next few implementations. The second one we will look at will involve saying, let's not search through all the row 1 stuff to get to the row 3 stuff. Let's try and index by row so we can get to these row 3 things faster. And this is known as the row list implementation. And there'll be an analogy to store by column, which will be a column list. So these two are really basically equivalent implementations. But we'll look at the row list first. So the idea here would be we'd have a pointer to a list of rows. Maybe row 1 has some nodes, and row 3 has some nodes, and row 5 or maybe row 15 has some nodes, and say that's it. So we have a list of all the rows that actually have meaningful elements of some kind. And then we have, off of each of these nodes, a pointer to then the corresponding list from the singly linked list. So perhaps here I have 1, 5, and then here's my data. So the data had been x. And then we have here 1, 8, and some data. And maybe that's the last element in that column, or last row. So there we go. And then maybe there's only one element in row 3, but we have here 3, 1, h, and then a null there. And then however many that had, and so on. The idea being each of these is one of the rows of the array, and instead of chaining them all together in one large linked list as we did last time, we will instead have a separate indexing list that will store all the rows, and off of each of those nodes we have a pointer to the appropriate row. So we could arrange things that way, and that's known as a row list. The column list analogy would simply be saying, let's have a list of all the columns in our array, and then each of them would point to all the rows in that column. So I'm not going to really say anything more about that, other than the situations will be parallel, but that would be the column list idea, that's the row list idea. And they're basically the same concept, just swiveled 90 degrees. Now, one of the things you may have noticed is we don't really need to store all the information we've got there. Once I hit this row and I start saying, oh, row 1, that's what I want, and I start traversing across this, I know everything in this list is row 1 because I wouldn't have entered this list unless I wanted row 1. I checked that number there and started traversing across there. So I don't really need to store the row number anymore. All I need is the column number. I establish it's row 1, and then I'm just searching down here for the pairing of the column number, which is the other piece of information I'm missing, along with the data. But the 1 can be assumed by virtue of the fact that we're in the row 1 list. So what that means is we save that integer every time. What we have here now is we only need 1 int, 1 pointer, and the data per cell. So for every cell we're representing in the singly linked list, we needed 2 indices, a pointer and a data. Here we need only 1 index, a pointer, and a data per cell. But then in addition, we have plus 2 pointers and 1 int extra per each active row. That is active, by which I mean it holds meaningful elements. So that's these here. So what I'd like to tell you is the 4 implementations that we look at will progressively become faster or better access, and will progressively use more and more memory. That would be a very nice continuum to say the ones that have the worst access have the best memory usage, and the ones that have the fastest access also use worst amounts of memory, up to the actual real array itself, which would use the most amount of memory but also have constant time access. That would be a very nice thing to say. However, it's not entirely accurate. The reason being that under the right circumstances, the row or column list might indeed use less memory than the singly linked list. The key is here, I'm saving a bunch of ints, 1 per cell. Now, if the number of cells is such that the number of cells here that I save is greater than the number of cells I use by saying, per row that is active. Or in other words, if the number of cells I have is more than 3 times the number of active rows, I'm saving 1 int per each cell, but the number of cells is more than 3 times the number of active rows, and I have 3 memory cells per active row. In that case, then I would be saving more memory with this implementation than I would be in the singly linked list implementation, because I have more memory saved by tossing those integers out than I would be gaining by needing the row list. So it all depends on exactly what the layout of our data is and how much data we have. But under some circumstances, the singly linked list could take up more memory. Under some circumstances, the row or column list could take up more memory. And so which one uses memory better simply depends on the general layout of your data, how much data you have and what rows it's in, and so on and so forth. What we can say, though, is that access is definitely better here. So we do have the idea of saying, as we look at new implementations, access improves steadily, because the idea here is if this is our, let me just kind of roughly sketch this out again. Maybe we have 3 elements down here. In order to find a particular value, I have to search down the row list and then across a particular column. So in the worst case, I have order R plus C for lookup time. And unlike the singly linked list, which would probably be a fraction of order R plus C, we could actually end up worst case with order R plus C. Probably we'll end up with a very few elements to look at, just like the linked list. So the linked list is potentially very bad. I'm sorry, the singly linked list is potentially very bad. The potential here for how bad it can be is a little bit better. But we can indeed have a very high constant for this, simply because if by coincidence, even if we have a sparse array, if we have an arrangement like that, where the values are arranged in an L and these are all null elements, then I might have to search down the full number of rows and across the full number of columns, where the very bottom column, the very bottom row has all the elements that are possible, where each of the other rows only have 1. That would definitely be order R plus C. But then you look at that situation and you say in all the other cases, then the lookups for the others would be relatively quick. So in general, this can be potentially faster than a linked list, which would require searching through every element. Here, we almost have to look through every element anyway, almost. We won't quite be traversing down these rows, but in general, this would provide better lookup than a linked list would for the same set of elements, because we simply can skip over. I don't need to, if I want to read this element, look at all of these and all of these. I can simply do 1, 1, and come down here. So your row list or column list will tend to be better in that respect. However, there's one thing to notice here, which is that that works fine for looking up an element. It also works fine for iteration in the best direction. If I want to iterate across a particular row, I simply need to find that row and then traverse across it. That will still be order R plus C. If I want to iterate in the worst direction, for example, if I want to find all the column 5 values, and if this is a column 5 value and so is that and so is that, if I want to traverse down column 5, that's a problem because I don't have any means of jumping from here to here to here. What I'll need to do is traverse across the top row to find 5, traverse across the next row to get 5, traverse across the next row to get 5, and so on. And if I'm doing a order C, potentially order C traversal for each of our rows, this is potentially, in the worst case, R times C. Probably a little less than that, but worst case would be R times C. So for the row list and the column list implementations, we often want to iterate across a row in an array or down a column, and this is where these start to be a little bit worse than the next implementation we'll look at. The iteration in the appropriate direction, for a row list, iteration by row, for a column list, iteration by column, will be R plus C, but to iterate in the opposite direction, to iterate by column in a row list implementation or across a row in a column list implementation, that would be order R times C. And so the next implementation that we want to look at is known as a multi-list or a threaded linked list, and that tries to eliminate that problem, but it uses more memory. Multi-list, or sometimes it's called a threaded list. And the idea here is you have a list of all appropriate active columns, and you have a list of all appropriate, all active rows. So maybe that's all the active rows we have. In addition, you of course then, in addition to storing what row it is or what column it is, so you have basically 2 pointers and an int for each of these. You have the letting you know what row or column it is, and then you have pointers to the appropriate row or column list. What that means, though, is that now let's say this is 1 and this is 7. 1 comma 7 meets right here. And then maybe this moves to here. And let's say this is 1 and 8 and 9. And let's say this is 2, 7, 10, and 16 for rows and columns. I drew the pictures too small to write the numbers in there. So let's say this is rows 1, 8, and 9, columns 2, 7, 10, and 16. When we start drawing these out, we may well have a situation like this, where now we have maybe 9 comma 2 has a node, and perhaps now 9 comma 7 also has a node. And maybe that's the last node there. 8 comma 16 exists. 1 comma 7 exists. 1 comma 10 might also exist. And in fact, perhaps, well, that's how we drew here. So if I wanted 1 comma 16 to exist, I would then have another node here, and 1 comma 16 would point to here, and that would point downward. So the idea is here I have the list of everything in row 1, everything in row 8, everything in row 9, everything in column 2, column 7, nothing in column, or maybe this should be in column 10, and then everything in column 16. However, unlike the row or column list implementations where these were all independent, here I have a given node as part of both the row list and the column list. And therefore, I need to store both indices again. So given one of these nodes, let's enlarge this one, would look like this, where I would have here 8, and I'd have 16, and then have my data. So this is my data. And then I'd have a pointer downward, which in this case would be null because it's the last node in the column, and a pointer across, which would also be null because it's the last node in the list. But I need 5 pieces of information for each node. The reason we once again need the row as well as the column, you might be inclined to think, well, now I've got lists in both directions, I don't need either of them. But the answer is we need both of them because we have 2 directions. If I'm going to traverse down column 16, I need to know what row I'm in. I can't say, oh, I assume row 8 from the fact that I was here. I was never here. I came to column 16, traversed down here, and I need to see, oh, this is row 1, this is row 8, blah, blah, blah. But likewise, if I'm going to traverse this way, I need to see, this is column 16, a node here would be column 7. So I can't assume I'm coming from a particular direction like I could with a row list or column list. Therefore, I need to store the row in case I'm traversing by down column. I need to store the column in case I'm traversing across a row. So we once again need both of them. But the idea now here is to find a particular value would be r plus c in either direction. Across a column, down a row, or down a row, across a column. So look up now in 2 different directions will be order r plus c. And iteration in both directions would again be order r plus c. Down a row, down to the appropriate row, across the entire row, or to the appropriate column, down the entire column. So iteration works r plus c time both ways, and lookup is r plus c time, and you have 2 different ways of looking up now. Down the row across, or across the column and then down. And then we see here, what I have is 2 ints, 2 pointers, and a data for each node, plus I have here 2 ints, 1 pointer for every active row and column, because I have these the column index list and the row index list. So I'll have 2 pointers and the index to hold the row or column number for every active row and column. So I'm using more memory now than I was before. But on the flip side, we gained some speed improvement for certain operations. So that's a multi-list, and inserting into it can be kind of interesting. You basically need to traverse down both lists. If I want to insert here at 8, 7, I need to traverse down and get this pointer, and traverse down to column 7 and get this pointer, and then say, here's my new node. I will point this to here, point this to here, then change this pointer to point to here, and change this pointer to point to here. So now we will come like this, down there, 8 points to here, and that points across. So it's basically running the linked list insert operation, but in two separate lists independently. That's all I'll say about that. And finally, we have the hierarchical table. And all this is a fancy term for dynamic allocation of your subarrays. So you can do that in C++. We talked about pointers and how a pointer to an element is the same as the starting address of the array. We can do that for multi-dimensional arrays as well. So just like I could say int star x equals new int 6. And in that case, x would be pointing to a dynamic array of length 6. Likewise, I could say int star star x, and then x equals new int star. So here I'm saying I have a pointer to an int pointer, and so my int type is mine. Just as we had type was int there, those parentheses shouldn't be there. I'm just showing you something. But the idea is when I had an int pointer, that meant I pointed to an array of ints. When I have a pointer to an int pointer, it's because my array is of int pointers. So we have a type match there. Whatever I point to, that's my array holds. If I point to integer pointers, then my array holds integer pointers. And I can say new int pointer of 6 there. So this line would have really been, let me remove the parentheses, x equals new int pointer of 6. And then I can say for int I equals 0, I is less than or equal to 5, I plus plus. And here I can say x of I equals new int of 5. So if I have a 6 by 5 array, there's my two-dimensional setup. I use this list to do it. I declare a double pointer, point the pointer to a new array of int pointers, and then each int pointer points to a new array of integers. So what I have effectively accomplished here is, and you can see on the new slide, what I've done here is now x is a double pointer. It's a pointer to pointers. We allocate off of that an array of pointers of size 6. So 0, 1, 2, 3, 4, 5. And each of these will be a pointer. And then we use the loop to allocate off of each of these a pointer to a dynamic array of just ints, where here is 0, 1, 2, 3, 4. So that's how we would allocate dynamic multi-dimensional arrays. And because of the way the bracket operator works, indexing works exactly the same way. If I want x 0, 3, that would be how I would access this element. If I want to write, say this is integers and I want to write 5 into there, well, what we're saying here is x of 0 gives you whatever's in this cell, as well we've seen many times before, but what's in this cell is a pointer. So then that pointer can be used just as x was a pointer and we use 0 off of it. This result is a pointer, and we can use 3 off of that, and that gives us this cell, and we can put 5 there. So that line, x 0 in brackets, 3 in brackets, is how we would use dynamic multidimensional arrays in C++. What this means, however, is that I have the ability to not allocate whatever arrays I need here. So if I say, for example, that I only have stuff in the first row for now, these could all be null. I can forget about this loop part and forget about allocating all of those and simply have an array that looks like this, where I have here many null elements here. And I just simply allocate this particular array, and here's 0, 3. When I want to access 1, something, that requires I allocate the whole row. When I want to access 5, something, that requires I allocate the whole row. But I don't allocate the row until I need it. So all this really is we're dealing with a dynamic array situation, but we don't allocate the individual extra portions until we need them. When I insert my x would initially be null. When I insert my first value, that's when we create the index dimension 1 index, and along with creating whatever else I need. And then I add the dimension 2 indices as I go. And that would be the idea of a hierarchical table. I can extend that to multiple dimensions very easily, so we can imagine an array that looks like this, where I say initially x is a triple pointer, int star 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 x. So x is a triple pointer because it will point to an array of arrays. And so with my first, let's say I say now x of 0, 1, 3 equals 7, well, x was formerly a null pointer. Let me write it better out. And when I do this, we first say, well, x points to null. So let's say then our dimensions were 5 by 4 by 3. That means this should be 2. So 5 by 4 by 3. And so 0, 1, 2, 3, 4. And that's my first array of 5. Now I need row 1, so that comes here. And I need to have 4 cells. These should all be null. I also need row 2. So here's 0, 1, 2. No, I'm sorry. Yes, 0, 1, 2, 3. I screwed this up. I'm sorry. Very sorry. We need our first array has to be of size 5. We want index 0 there, so that's what we want. The rest of these are null. Our second array is of size 4. We want index 1 from there. The rest of these are null. And then this will point to an array of size 3. And the rest, either we can write 7 in there and now have a default element here and here, or we could have had pointers to elements here as well. But the idea will be now, whenever we need an array, we have to access the entire array, and all the non-active ones then are then pointers to null. But this would then be a 3-dimensional hierarchical table where we only inserted one element. X now points to that array, and we've got that whole setup there. Now, the big disadvantage here is that we use a lot of memory. We're using less than we would have to, but I've got all this memory allocated just for one cell, and every time I need to insert anything in a row, I have to access or allocate the whole row, the whole array. So if our data is all bunched in one array or one area, that's really good. But if our data tends to be sparse, but spread out all over the 3-dimensional space or all over the 2-dimensional space, we'll tend to use a lot of memory with the hierarchical table. Because as soon as you need one element in an array, you have to access or allocate the entire array, which is a disadvantage. However, the big advantage here is we still have constant time. This is still an array. If I want to access 0, 1, 2, I'm simply saying x plus no offset, grab this array, then take that address plus 1 offset, brings me to this cell. That address plus 2 offsets brings me to that cell. I have basically 3 consecutive array accesses. Each one is constant time, so we have a total of constant time. Or in other words, what we really should say is order D, where D equals number of dimensions. But that is not going to ever change no matter how much data you have. So certainly you can input all the data you want. You still have basically the same amount of access time no matter how much data you insert. So the hierarchical table advantage is it's the fastest, and it also will tend to use the most memory depending on the distribution of your data. But it's very nice in that you can get constant time performance while still saving a bit of memory. I didn't need the full 3-dimensional space here. I only needed a little bit of memory to be allocated. So you can save some memory while also not losing your constant time access ability. And I think that's a very nice feature. If you need to save more memory, or if your data is so spread out that the memory savings of the hierarchical table are negligible, then this may not be the one for you. But if the data arrangement is such that the hierarchical table does save you some memory, if it saves you enough memory, then this would be the best way to go because you have wonderful speed. So it's simply a matter of whether the arrangement of the data serves you well or not. That's it for sparse arrays. I probably went over the 50-minute mark on this one, but you've got a nice amount of information here. I spent a little bit more time on some of the stuff than I may have whizzed through it quickly in lecture. And that's it for linear structures. The next 3 lectures will be on trees, as I said, and we will start those next time. So till then, I'll see you later.